In this section, we want to talk about what we call linear programming problems. So for these linear programming problems in this section, we are going to be finding a graphical solution. A linear programming problem is when you have a linear, what we call objective function, and that is the function that we either want to maximize or minimize. So that's always the goal, is to find the max or the minimum of something, some situation, subject to certain constraints. And so we saw in the last section, constraints are these linear inequalities that bound the feasible region. Okay, so we're going to find a feasible set that's similar to what we did, and then we are going to find the optimal solution to this problem. So basically, it's adding context to one of these linear inequality systems. So there are a few theorems that we need to know about these solutions to these types of problems. Okay, so the first theorem says about solutions that if a linear programming problem has a solution, then it must occur at a vertex or corner point of the feasible region. I guess I already had the word point. Okay, we doubled that. So if it has a solution, a max or a min, then it's going to be at one of the vertices. It's not going to be somewhere inside it, it's going to be somewhere around the corners. Furthermore, if the objective function p is optimized at two adjacent vertices of S, then it's optimized at every point on the line segment joining those vertices. In that case, there are infinitely many solutions to that problem. So if you happen to find two corners that both maximize it, then every point on that line also maximize it. Okay, theorem 2, the existence of a solution. If we are given a linear programming problem with a feasible set S, an objective function p equals ax plus by, then what we know is that if S is bounded, I should say then P has both a maximum and a minimum value on S. So one of those corner points will be the max and another one will be the minimum if it's bounded. If it's unbounded and both A and B are non-negative, so if all the coefficients are positive, then P has a minimum value provided that the constraints defining S include x is greater than or is equal to 0 and y is greater than or equal to 0. Now, that's not necessarily something that you're going to have to memorize, but it's just nice to say, okay, so if all these situations happen, if it's unbounded and non-negative, then it will have a minimum, as long as you have those two specific constraints. If S is the empty set, then there is no solution. P has neither a max nor a min. So if when you are drawing it and none of your shading overlaps in all the areas, if there is no place where all of them overlap, then you can't have a feasible region. So therefore you cannot maximize or minimize it because there would be no corner points in common. Okay, so the procedure that we're going to use in this section to solve these linear programming problems is called the method of corners. What we're going to do is we're going to graph the feasible set. So that goes back to the section we've just covered. We're going to get it all graphed. We're going to find the coordinates of all the corner points or vertices of that feasible set. We're going to evaluate the objective function at each of those corner points and figure out which vertex gives you the max or the min answer.